Hi everyone, can you see the screen? Just need your feedback if you can see the screen projected. Hi.
Yes, Victor.
Hi, David. Okay, thank you. Okay, so we're about to begin. Give us 1 minute. We're about to begin. Sorry for the bit of delay. So maybe Alex, if you're ready, we can go. Okay, you need to stand here, like within the view of this. You can see yourself here. Right? Okay.
Yeah.
So over here you can. The audience should be able to hear.
So if I stand here, can you hear me?
Should be okay. Should be okay.
Recording in progress.
Closer will be
Yeah.
clearer.
Yeah.
Okay. So Alex, you can come here then.
Yeah. Maybe I just use that one.
Okay, then check.
Yeah. Start from. Yeah.
So, Alex. So, good morning, everyone. Welcome to our organizer today, WCC Center, and also IEEE ComSec. And yeah. So, welcome to the V2X seminar series, a holistic design of vehicular networks, communication, blockchain, security, and Internet of Things. So we have our speaker, Dr. Zheng Guoshen from University of Sussex, United Kingdom. So our session will start from 11 a.m. to 12:30 p.m. And before I pass the mic to Dr. Zheng, let me introduce Dr. Zheng. So Dr. Zheng has been a leader in Department of Engineering and Design at University of Sussex since 2021. He received his PhD and master degree with distinction at Imperial College in 2011 and 2007, respectively. And his Bachelor of Science from University of Electronic Science and Technology of China in 2006. His current research interests power connected vehicles, Internet of Things, and cloud or edge computing. He has published over 120 journal and conference papers, 5 books, and 1 patent and 2 standard contributions in 1 M2M and OMA, WLWM2M communities. M2M means machine to machine. His current research works are funded by Hedge 2020, EPSRC, Royal Society, and University of Sussex. He's also the recipient of Royal Society Canton Po International Fellowship 2020 and Emerging Research Award 2017 from University of Sussex. Thank you, and let me pass the mic to Dr. Zheng. Dr. Zheng.
Thank you, everyone. Also, it's my pleasure to visit UTM once again. So this is my third time to pay my visit, and also my first time after a long period of pandemic. So I finally got this opportunity to join everyone and also with colleagues from UTM face to face. Okay, so the title of my presentation is about the vehicular communications. As you can see, the title is more focused on holistic design of the vehicular network, combining these communications, blockchain, security and services, as well as the Internet of Things. So yeah, this is about myself. So I will briefly just given that our host already mentioned about myself. So I'm currently a reader from University of Sussex. So my research area is in vehicular network and communications, and also I did have my research basically as a postdoc from the University of British Columbia, And also our labs done 2 years industry researchers, and also got my master and PhD from College London. Just one slide briefly about my university. So University of Sussex is on the very side, south side of the UK. As you can see, it's very close to London, in the city of Brighton. So we are top 20 in the UK, and also the top 50 in Europe. So we do have 3 Nobel Prize. Also, most of them are from chemical and physics areas, but also have like 14 Fellowship Royal Society and also British Academy. Right, because the topic is more about the vehicular communications or connected vehicles. So probably some of you may have this quite a simple question: what is basically the connected vehicles? Right. So here I just give one slide overview of what is definition. So basically, the connected vehicle allows all nearby vehicles to exchange, right, the data of their positions, right, speed, directions, and also there's very rich for data that beyond this simple parameters, as you can see, that can be exchanged, right? So this is no upper limit of what sort of location data that can be allowed to exchange between vehicles. Certainly, the applications you can imagine, including more drivers or potential collisions that are not visible to sensors, because we are now probably in the era that most of people see a lot of new electric vehicles, right? So autonomous vehicle on road. A lot of potential new car manufacturers invest a lot of money into these domains. So most of their solutions are more focused on this sort of physical sensor, no matter it's a LiDAR sensor or even the camera, right? To measure the distance or maybe a line of sight, right? Visual distance to avoid any potential collisions. But connected vehicle can further beyond reaching connectivity, because once you connect it with the vehicle, you can imagine some information, right, can be reached in multiple fashions. So in some potential applications, as you can see, few videos on the bottom, including vertical lane changing, controlling. Certainly, the car can receive instructions, from third car who's leading the platooning, and they can just follow the line and also keep the speed, informing kind of regulated transportation, right, system. Or in the middle or on the right hand side, as you can see, is more like a complement. What sensor cannot be done is to inform the drivers, for example, of a disabled car have out of sight, right? Because once you have this curve or some non-invisible scenarios, the sensor cannot really help much. So in that sense, if the vehicle that can communicate each other and also combine it with other types of data, for example, your location data, or etc., or speed data, so the warning actually can be given ahead of time, as you can see from these 2 figures, is that when you have the blind spot, so basically the communication can help to avoid the potential collisions. So strictly speaking, so when we talk about vehicular communication, there are 2 types of communication. One is the vehicle to infrastructure. The second one is the vehicle to vehicle, right? So behind these 2 types of use case, certainly we have different technologies that need to be applied. In this case, it's a vehicle to infrastructure, which means the vehicle can talk with the transport network, for example, traffic light, right? So in this, as you can see, right hand side is this police car or emergency car. They can talk directly with traffic light, so the traffic system can optimize basically the traffic throughput and give more priority to these emergency vehicles, right? So this is basically the communication between the infrastructure with the vehicle. The second one is basically the vehicle to vehicle. So in that case, we don't really rely on the infrastructure. So the vehicle themselves can talk to each other, not only just between vehicle and also with pedestrian, right? So in that sense, these sort of early warning or some traffic incident message disseminations can be sent directly to the nearby vehicles to warn them that there's, for example, potential collisions, etc., and you can choose another detour, right, to drive your car rather than relies on the central authorities to send all these messages to the individual driver. So this is potentially basically two types of use case behind connect vehicle. One is the vehicle to infrastructure, and another one is vehicle to vehicle. Certainly, behind the vehicle to vehicle, the most dominant vehicular communication technology we talk about is more like a Wi-Fi type of solutions. In the industry side, we define them as the DSRC, which is dedicated receive near-field communications, which is dedicated for the V2V communications. The second one is, as you can see, is the V2I. So this is more relevant to the 5G or even 4G and new region or V2X communication standards. So as a brief summary of the vehicular technology on this slide, we just show what the vehicular network architecture looks like. So from our point of view, is that we, as you can see, is define our vehicular networks into 4 domains, right? So we believe that the vehicular, when we talk about vehicular communication, is not only just wireless communication, right, between vehicles, because you need to imagine where is already data coming from. Certainly, the data is coming from the vehicle themselves, right? So the first part is the in-vehicle domains, right? So because now the vehicle itself is a very complicated ecosystem, right? So there are many different subsystems, for example, engine system, or even exhaust system or chassis system, etc. So each of these systems, they have different sensors, can generate sensor data, and this is the data need to be somehow transmitted, right, or coordinated within the vehicle, right? And then certainly we do have a central gateway, which means that can enable vehicle with other vehicles in a wireless way, right? So this is the first domain, is to have an in-vehicle communication ecosystem, right? And then when the vehicle is running on road, certainly it relies on other wireless solutions. For example, with the infrastructure, the 5G power, this is more V2I infrastructures, right? So this is more relevant to the V2X and the physical layer communication and security. Okay? And also, once we have this communication platform that we established, we need to look at also on upper layer, which is the big data, right? So how the big data can be managed, right? So this is really depends on the type of services we're looking at. So one part is that we probably rely on some central server. So that sense is based on some big data, basically applications to manage the huge volume of data that is collected from the vehicle server, right, down to services to individual vehicles. So from this domain, so we think of it as just general data-centric securities, which basically relies on the infrastructure or relies on V2I communication infrastructures. So on top of that is the blockchain services. So the services is basically one utilization of this data-centric network is to look at more distributed data utilizations across all the different vehicles. So this is more referring to B2B communication systems, right? Is to how to look at how blockchain can contribute to security in a more distributed way. So from different communication levels, we think that these 4 actually research domains to be well complement each other to fulfill a full vehicular network ecosystem, right? And also considering both communication and also security. So in the following, I will highlight. Okay. So in the following, I will highlight some of our key research work across these domains. Okay, so the first one is about in-vehicle networks. So I'd like to just briefly go through some background of in-vehicle network, which is the evolution of automotive electrical and electronics architectures. So from the very beginning, when we have our cars, right? So our car is more like a fully mechanic space, right? So I can see, for example, when we have the car widely being used or on the road from 1950s, by that time, we don't really have very complicated electronic system. Yeah, probably we only have a few electronic components, for example, the light, or maybe the turn on and off your brushes or wind brushes. So in that case, as you can see, the communication is very simple. It's only just support some peer-to-peer communications. There's no interactions between the systems, right? So in that sense, we don't really need to have too much interactions between systems. But gradually, when we have more X-by-wire kind of being applied into our vehicle, which means that we rely on the electronic component to control our vehicle, no matter you start engines or maybe you steer your wheels. So that's basically all being controlled by electronic system. As you can see, the topology of in-vehicle network is expanding, right? And it will be more complicated from the peer-to-peer to the bus system, and then towards the central gateway, involve Ethernet as a backbone, and to more domain and zone-based services. So for the zone-based services, it's more relevant to the software-defined network, and also this edge computing type of techniques can help basically the vehicle domains to make their own individual decisions. So this is more relevant to the modern smart vehicle or autonomous vehicles type of features. So as you can see, certainly the challenge is that because we have lots of sensors, right, lots of electronic systems, all these components and equipment, they need to be connected by the wire. So the wire is not only just power the component, it's more communications, right? So this is what it looks like. So if we only utilize these peer-to-peer cables to link all our car electronics, certainly this is not really a decent way to deal with the whole in-vehicle network architecture. So this is probably a more modern looking of the in-vehicle bus network architecture. As you can see, that we rely on some very nicely set up this platform buses mainline, and also to connect them with different subsystems. So this is a typical case of a Tesla, the modern electronic cars, or maybe autonomous vehicle cars that you can look like. But nevertheless, so the challenge, as you can see, is that because we rely on this full EE architecture, or this is being adopted by the industry, is to look at electronics, right? And also with a significant amount of connectivity that be implemented in the future cars. Certainly, the challenge is the complexity and also the cost of all this in-vehicle data connectivity, right? So here I give an example. So for a traditional wire harness, right? Because I think for the in-vehicle network, still the default standard is to use this wire communications, right? So the challenge actually can be outlined from the three aspects. So one is the complexity, right? So certainly we talk about our vehicle, modern vehicles, more than 4,000 parts, right? So if we line up all this communication cable, it's more than 2,000 wires, and also the length is more than amount in length, right? And also it's a heavy. So all these communication cable, you put them together, is the service, heaviest and costly component in a car, right behind the chassis and engine. So this is something that you never probably think of. Wow, why the communication cable takes so much space? And also certainly it's costly. So from car manufacturer point of view, they want to reduce the complexity and also reduce the cost. So this is the traditional, the challenges that faces from in-vehicle domain. So the question is that, is there any way that we can reduce the complexity of the cables, and meanwhile can maintain the connectivity inside the vehicle? So certainly there's one solution probably people have heard about is the power line communication, which means that the communication can be delivered over the power wire. So in that sense, you can eliminate or reduce the number of the data wires by just simply relies on a single power cable to drive the electronic control unit or any sensors. So I just want to briefly highlight the state of art of this wireline communications. So the power line communication itself basically has been proved and also developed as a feasible physical media for data communication. For example, the home plot is the one of the biggest alliance to standardize the power line communications. So this is a dedicated version, which is GP, which is a GreenFi. Basically, it's a lightweight solutions for the future Internet of Things driven by the power line communication. So power line communication itself is the relatively mature communication technologies. But the challenge is that the power line not being considered into the vehicle domain. Usually, the power line is used in the buildings, right, or well stable network infrastructure, because the vehicle is more like dynamic network with dynamic network scenario and also this radio environment. So the challenge is with new demand in network technology to achieve mission critical communication. And also the vehicle have this so-called mission critical communication requirement from the following 5 aspects, including reliability, priority, latency, throughput, and internet working, right? So I just give you one example. As you can see, it depends on different type of in-vehicle traffic. As the control data, the maximum end-to-end delay is 2.5 milliseconds. So how can we use, for example, the power line communications to achieve such a low end-to-end delay performance? Is the critical thinking behind the application into our in-vehicle domains. So I like to stick with this end-to-end delay, because this is the one of the critical criteria behind this mission critical application, particularly for the in-vehicle domains. So I just want to give you understanding, for example, the mapping between the typical in-vehicle power system to network topologies. Right? So the vehicle itself, the vehicle is primarily driven by the main batteries, right? The main batteries, and then we'll split into high power battery junctions and also the standard battery junctions. So under different categories with different subsystems will be power, right? And for under each power system, subsystem or each component systems, so you will have control ECU, which is electric control unit, to coordinate different sensors. Yeah. So in this case, we have throttle position sensors, air temperature sensors, and also speed sensor. Be connected behind this engine motor subsystem, right? So this is more theoretical structures behind the vehicle power system and how linked with each ECU or control unit electronic system. So if we map it into the data network, as you can see, is that all these 3 sensors has been actually connected with a single control unit. Yeah, and then cross a switch. So the switch probably is more somewhere here to interconnect with other box systems. Because, for example, if we have a system here, engine motor, need to coordinate or exchange signals with other non-emergent systems, other domain systems. We need to rely on a switch in between, right? So this is basically how the data flow are interconnected under this main power basically system topologies. So one easy way to define this end-to-end delay is to have these 3 components, right? Access delay, transmission delay, and queuing delay, right? So this is easily identified from these data network topologies, because you do have a number of sensors to compete each other, right? So they are basically the same systems. So you do have this access delay, and also once you got the privilege to transmit, then you have a transmission delay, right? It depends on what's the size of the packet and also your transmission data rate. And of course, you also have queuing delay, especially if you are passing through a switch, right? The switch need to serve multiple subsystems or control units. So this is a typical 3 component if you talk about end-to-end delay. Okay. So now we're going to look at how can we characterize this 3 component delay by using the network calculus. So basically, network calculus is a mathematical tool that can basically give us the worst delay performance of this basically access delay, the first of all component. So network calculus is the deterministic modeling approach, right? To analyze congestion control of the switch Ethernet. cellular network and also machine-to-machine and other Wi-Fi solutions. So the essence of this network calculus is to define these two curves. One is the arrival curve, and the second one is the service curve. So the arrival curve basically is the cumulative the volume data that be generated. You can assume if this is the black box as a single transmission or sensor node. The arrival curve is how much the cumulative data is generated by yourself as a sensor, right? So you need to characterize your arrival curve using mass spectrum formulation. So we use this token bucket controller concept, which is the minimum between these two components. The R is the maximum bandwidth, right? Multiplied by time, or we use the CCAP plus this row line multiply T. So the CETA is basically a burst data. So the burst data can be just a single packet length. So this row line is basically average rate of flow, right? So the flow of a sensor node. The flow is Li divided by Fi. This is the frequency of transmission, and this is basically the length of your packet. So the arrival curve can be characterized by this formula to get a minimum value, right? So this is accumulated, as you can see, because you have rate and multiply times. This is how much data be generated from time 0 until time t. Okay, and also you have a service curve. Basically, it's how fast data can be served. One side you have data into the black box, another side you have the data going out of the black box, right? So this is data curve is served by bandwidth, yeah, with latency, right, which is capital T, yeah. So the T is a waiting time because you consider in practice is that you have a higher priority load rather than yourself, so you need to wait for the time your time, and then before you can be served. So let's see how can we use these two curves, arrival curve and service curve, to derive the access latency. So I just want to draw your attention to the figures, right? So basically, this figure you can see there are two curves. One is the arrival curve, another one is the service curve. So the arrival curve basically, like I said, is the total amount of data that is generated by these let's say transmitters. Okay, and the service curve is how much data the transmitter can get access into the channel to push its data right into the transmission channel. So this is the two curves. And then what is the delay or the worst delay? Basically, the worst delay or the maximum delay is the maximum distance between these two lines or horizontal lines. Yeah. The reason because this is the cumulative, right? This is cumulative input data. This is cumulative output data. Certainly, the same data will happen across this horizontal line, right? And then this the gap, the distance is delay. So we only need to measure the maximum gap between these two curves, and then this is basically the worst access delay performance that we can calculate from this basically the series, yeah, network techniques. So certainly is that we find a way to get this maximum access delay time from this network calculus, and then get the result by using the whole plot verified. Basically, is a standard into a Vehicular network, and then we can get this maximum transmission delay. Upper bound is 2.1 millisecond. Yeah, certainly in this equation there are a number of variables, but all these variables are related to this basically individual data rate of each priority flow, and also depends on number of priorities, as well as the packet size and bandwidth. So here I think we just need to have a sort of idea that basically this access delay can be characterized by using the series. The second step, because now we know what is the access delay, so simply we're also interested in looking at the queuing delay. So queuing delay is that when you have a different data traffic that we arrive at the same switches. So how do we prioritize? Right? Because each of these data, they have different priorities and also the latency requirement. So how do we satisfy to deliver all this data within the deadlines? So this is basically involve the delay sensitive traffic shaper, right? So the traffic shaper means that the data can be given different priorities when they arrive at the switches. So if for certain, let's say, priority values with more urgent deadlines, they will give a more high priority to transmit. So they don't really need to follow this first come, first serve at the switches. It really depends on the budget of the delay deadlines. So we use these two slots to regulate the gain critic and also reducing critic. So as you can see here, once a node is waiting, right? Let's say this is the delay time, access delay. So once for a single node needs to be waiting for the T prime time period before it can be served. In the meantime, all these waiting nodes, they are starting to gain their critic, right? Every node is gaining the critic until they basically start to transmit. So basically, this is the time point that they are the highest priority node, and they can transmit on that, and then they can have this reducing critic. To consume is basically the gain critic. So this is use this kind of way that we can dynamically change the priority of different transmitters across a single switch to make sure that all nodes they can be served with basically a right time and the right amount of time budget. Make sure every node can satisfy or reach their delay deadlines. So this is the performance evaluations. As you can see on the figure left-hand side, it shows the maximum delay of this power line communications compared with the standard inbox, CAN-box, or multi-CAN-box. So this is more standardized individual because, as you can see, the delay performance is comparable. Yeah, no matter you have a lowest priority or highest priority, delay performance is comparable with all these traditional CAN-box, and also much better than the inbox, which is not really a real-time driven solution. So from the right-hand side is that we further consider this traffic shape-up when we consider end-to-end delay performance. On top of access delay, and also we have queue delay and the switch transmission delays. Right? So in this example, we have 7 priority levels, and also for each priority level node, we assume there's the target end-to-end delay budget. So this is deadlines for each priority level that is specified. So our proposed solution can satisfy all of this budget for the delay deadline requirement. But for other industry solutions, as you can see, there's some values that put as a start, right? Just telling you that in this case, certain level of priority cannot be satisfied, right? Using each of these single solutions. So in this case, we just assume a simple topology with one basically main network connected with switches talk to another network. But I think I just want to give you a quick highlights of basically what basically in vehicular network people are looking at is to look at the delay performance, right? Okay, so how can we use it? So now we understand that delay performance is critical for in-vehicle network, but in practice, it's very difficult to measure. Yeah, because the vehicle is a very closed ecosystem, so it's not like an open wireless network. You can dismantle your vehicle and use a prompt to detect all the link level performance. So this is not the case because the vehicle is very restricted. No one really has this access into the vehicle besides the car manufacturer itself. So if you want to measure the enter delay inside the vehicles, how can we do it? Given the difficult to access a closed in-vehicle system and also monitor every network elements and overburden networks. It's very complicated. You don't really know exactly the topology inside the vehicle. How can we do it? But we need to understand whether the in-vehicle communication that has been satisfied, right? In order to infer any consumer malicious attack or security issues, you need always monitoring your vehicle traffic situations. So there's a very interesting tool which is called network tomography. So basically, this is the one theory that can be used based on the end-to-end measurement, and we can infer the link level performance. Given that we don't really have a full knowledge of the topologies, but we still can infer about link level performance based on the end-to-end measurement. So regarding to the net tomography, so there are actually a number of categories, right, behind this series. For example, you can infer a whole topology, or you can infer this pad level performance, or even the link level, right? So there are also passive and also active tomography. Passive means that you don't really need to get additional measurement data, so it only relies on the existing traffic to infer the link level performance. Or the active means that you need to inject this kind of monitoring data on top of the standard or this traffic data. So this is a different way that you can do the measurement. So let me just give you a simple example of how we define the vehicle. So this is a vehicle topology, right? On the right-hand side, we will have a number of end nodes. We can say N1, 2, and 3 are end node, and also we have a switch in the middle, right? So a switch basically connect all these nodes with 3 links, E1, E2, E3. So we define the inverted network as a G, right? So the vertex and A. Vertex is the node, right? H is the link. So there are 2 types of vertex. So one type is the node inside the network. For example, this S1 is the node inside this R. So this node is a dimension larger than or equal to 2. Dimension is number of links. So you can see in this case, this node has 3 links, right? So this is basically the internal node. And also we have H node, yeah, which dimension equals 1, which means that there will only 1 link connect with this node. So all this H node basically are H node, right? With dimension equal to 1. So our goal is to estimate all this link level performance of each link E, right? So we want to estimate what is delay performance, right, across all this. And what we can do or measure is the end-to-end delay, right? So end-to-end delay, as you can see, basically is just a summation of the link level delay across the single path. Let's say if we want to measure from N1 to N2, so we just need to add these 2. Yeah, so this is 2 components across this path. So this is how the end-to-end delay is formulated. And then we can just write in a more type of map is y equals a times x. So y is the path measurement. So it's end-to-end delay. So x is the link level delay performance. So A is basically a matrix. A times gamma is matrix with element equals 1 if the link is this across the path, or is 0. So if we map this definition into this problem, as you can see, the measurement path has 3 paths, P1, P2, P3. So each path we have different link combinations, right? Path 1 including E1, E2. So this is one path. Second path and the third path we listed there. And the matrix actually shows which exact link has been used for any of this end-to-end measurement, right? So this is an easy way to define this kind of a matrix, especially the measurement matrix, of how the link has been combined with each other to contribute to one specific end-to-end measurement. So the first problem I want to define is so-called network identifiability, which means that by having the end-to-end measurement, how confident the link level delay can be measured or inferred, right? So we call it identifiability. So we have the similar equations, y equals a times x. So this is basically a network that we are using. So we say this inverted network G is identifiable if the link tribute delay for all links is uniquely identified. Or if we have k smaller than gamma, which means that we have basically a less number of links rather than the measurement. number of end-to-end, less number of end-to-end measurement rather than links, then we can't really say the whole topology is uniquely identifiable because there is some dependence across at least the two layers. So in that case, we can say the network would be a K identifiable, given that smaller value to just K and gamma. Or in total, we can say a network is totally unidentified. So how can we understand this sort of statement? So we can use these two figures to find out, right? So simply this is the one topology, right? And certainly we have H node, 1 and 2, and 3 and 4, right? So no matter how do you do the measurement into the measurement of this 4 node, you see these two links are always bonded together. So there's no kind of dependence between these two links because all the traffic has to go through these two links. No matter which two measurement nodes that we want to measure. So this can be easily mapped into this matrix topology because these two elements, E3 and E4, are always the same. Yeah, across all the measurements. So in that sense, these two cannot be differentiated. You always think this is actually combined together. It's a sum delay, so you can't separate them. So this is the second case. As you can see, across all the links, there are similarities. Yeah. So this, for example, from N2 plus 1. So these two links always bond together. When you do the measurement, these two always bond together, and these two as well, and these two as well, and these two as well. So from this measurement, you can see under the same colors, these two links are always bond together as the same. Yeah. So across the same color means that we have the same basically elements that always be bound together. Yeah. So this basically tell you there's no really independent measurement can differentiate between each other. So this is more like we calculate the rank of this matrix. Okay. So in that case, for this network, so we can get this 4 identifiable, which means that these 4 links can be identified. But these two cannot because they are always bounded in middle. And for this as well, the same colors actually has to be bound together. So how we differentiate the performance between E1 and E2? Yeah, so this is the same case as well. So in this case, it's totally unidentifiable because not all the links can be identified. Right? But in this case, E1, E2, E5, E6 can be identified because they are separate links, but not E3 and E4. So this is, you can assume this is a single link treated instead of 2 because they are always bonded together. So this is basically the network identifiabilities, and then we are basically come up with a decision and also conclusion. How can we, what sort of topology that we can treat it as identifiable, right? So we put this as topology conditions, which means that we need to have at least no return node have a dimension larger than 3, and also number of monitoring nodes. Monitoring node basically is the age node. So in this case, the age should be the maximum number of monitoring nodes to come up with a full identifiability. So this is basically the conclusion. One more statement that we need to look at is identify whether the network can be measured using tomography. Certainly, in some cases, like I said before, for this typical vehicular topology, we can't really fully identify all the link level with performance. Especially for these two, E3 and E4, they need to be always be bonded together as a single linear measurement. But how can we separate them? So here we just further consider using a neural network. Yeah, given that some part of the network not be identified, right? So for that particular situation, we use neural network or AI approach to help. But for the rest, if we use this type of network properties, we can solve them as the first step. So instead of infer all link level metrics, we can infer part of them based on available measurement. So Certainly, we need to have this network at least with 3 edge nodes in order to have a proper measurement. And also the measurement number must be more than 2. So this is basically conditions that we need to satisfy in order to use network topology as the first instance. Yeah. And based on that, you can further apply the neural network. As you can see, so this is pretty much the topologies that we basically use to apply our neural network. Is that we feed our network into this neural network. As you can see, the input is yi to yk. So this actually is the input measurement that you get from the raw data. And also we have this xi and yxj. So this is basically output from this result that we can get level from the network topology. So for this identifiable links that we can solve, right? In the first step, we use tomography, and then we put that as input of the neural. Just leave the unidentified link as output. This is basically something that we need to calculate. So you can see this is input into our neural network, and then we have output. So the white output is basically for these two unidentifiable links. This is hopefully what we want to calculate or measure or infer as a link level for us. So we have this mean square error functions, basically to benchmark the difference between the real output and also your predicted output. So this is more like a training process, right? Using the training data to minimize these mean square errors, and then feedback into the neural design to justify the weights across different hidden layers. So this is basically the key concept that we like to highlight behind this work, is to utilize the network tomography to infer some link level performance that can be identified. Yeah, depends on topology, and then lead the unidentifiable links into a neural network-based approach. So in that sense, we can fully solve the individual network delay performance across all links. So this is the performance. As you can see, we put 2 vehicular networks. One is the pure CAN network, right? So the full CAN network is connected with a single gateway. And with the more complicated network that we have Ethernet network in the middle. Yeah. So also we compare our performance with OTIDX. So this is a de facto standard used by basically another papers. So the essential difference is that for this OTIDX, he used dedicated traffic to monitor each CAN data or in-vehicle data. Separate on top of the normal traffic, okay? But for our network tomography, we don't rely on this kind of probing data, right? So we just use the existing traffic to do the measurement rather than use some dedicated monitoring traffic to do the job. So the figure on the bottom left-hand side, it shows, depends on the number of monitors. The monitor is the number of edge nodes that measure end-to-end delay performance. And the y-axis is the probability achieving the identifiability. Certainly, this probability is the 0 from 0 to 1. 1 is that your network can be 100% be identified, right? So depends on different sort of topologies. If we just use a single canvas, certainly we have 1 or 2 monitors that should be sufficient to identify full network. But if we have a more complicated network, for example, Ethernet-based network, so probably the minimum we need to start at 4 monitor nodes, and then we can gradually increase our network identifiabilities. The figure on the middle shows basically the latency performance across different network topologies using different approaches. For example, no monitoring and also network tomography. So no monitoring means that our network doesn't do any monitoring. So there's no additional monitoring traffic, right? And also net tomography is that we just utilize some very largely monitor traffic on top of sync traffic. So we can see basically, let's say if we just compare the slow monitoring and also network traffic one, the blue one and the red one across different lanes from B1 to B4, as you can see here, B1 to B4, there's not much difference, which means that the overhead of our network tomography is quite negligible, right, compared with low monitoring solutions. But comparatively, we have this OTIS, as you can see. So the delay performance is significantly increased. That's because for this approach, we introduced this additional kind of probing traffic to monitor every CAN bus network message that is generated. Right? So this additional traffic will incur significantly latency. Right? So this is the benefit by using the network tomography and compare with Vehicular with no monitoring solutions. And also we compare this absolutely the arrows from these network tomographies. As you can see, we still have arrows, right, across different traffic. So this is from X1, X12. So we'll map all this Ethernet-based link travel performance, right, into these figures. What we can see is that the arrows between the infer delay and also actual delay is well below 0.174 milliseconds. So we know that the in-vehicle delay constraint is typically is about 100 below 100 milliseconds. So these arrows is almost negligible, yeah, compared with different delay requirement. So maybe you're going to have a question. So given that you use now tomography, why do you still have errors happen between the real delay, link delay, and also inference delay? That's because in the real network, different data, different sensors, they have different priority to generate their data with a different frequency patterns, right? Because all the traffic data are not generated at the same time, right? So there are always slight delay difference, but also in different type of frequencies to do the measurement. Maybe at one time we do the measurement, but that measurement can only be to measure will be valid for that particular time window. But because you also have the time transmission from other measurement nodes, right? Because the measurement also relies on the measure of other traffic. So in that sense, you can't fully have a fully synchronized or real-time measurement all the time, because all the traffic are trying to be dynamic. So that's why even using tomography, we still have error, right? But this error is negligible or tolerant, right? Compared with end-to-end delay performance requirement. So this is basically further looking at more complicated network, which is with the TSN, with the time-sensitive network, right? Which means that we consider not only just SI4, we also consider, for example, ABB and ASO211Q. So basically, the ABB is more real-time, time-sensitive network status is to give more high priority across all this traffic rather than using simply SI4. So without TSN, which means that this is basically all traffic is best network based approach. So basic performance basically reflect our neural network performance, right? So for example, we have different percentage of measurement, right? From 10% of total traffic to 70% of traffic. 10%, let's say, we only measure one single path, which is P7. Yeah, P7 is across these paths. So 70% is that we have all these paths can be measured. So generally, this is mean average percentage error. Yeah, that we can see the percentage error is significantly reduced. Yeah, given that we have more measurement in the network. So when you feed back into neural networks, you can significantly increase this performance, which is the mean percentage error. Okay. So from 10%, as you can see, down to almost less than 1%. Yeah, and also that's because we have more subset of measurement. Yeah, more input data you get, you have, the more training data you have, then you can significantly improve the accuracy. The figure on the right hand side basically shows the inferred data, which is, for example, via the app, also actual output data. So this is basically can indicate that the neural network solution is working pretty well to infer not only the link level but also the path level performance. As I think these two lines is quite overlay each other, yeah, through this neural network approach. Okay. So next, I would like to just quickly go through some of our V2X communication works. So far, we talk about is more in-vehicle, yeah, communication, which is about the wire communication. So I think most of the people are more work on this vehicular or V2X communication. So there are different technical solutions, as you can see from these topologies. We have the V2V, yeah, using DSRC, and also have cellular based or IoT V2X, new radios, millimeter wave, right? So it's really heterogeneous vehicular network topologies. So the first work basically is also a learning based, which is reinforcement learning based DSRC. So we'll focus on the V2V, which is Wi-Fi based solutions, right? But with these solutions, there's no handshake or RTS, CTS that exists for typical Wi-Fi solutions. But for the vehicle, because of this real-time dynamic requirement, simply is more like broadcasting. Doesn't really require acknowledgement. But we do have this kind of conventional window size that dynamically can be changed. So our question is how can we optimize this conventional window size for each transmitters, given the consideration of traffic radio scenarios. So we use this reinforced learning. So basically, it's a learning approach. It's characterized by this multiple precision process, which include 4 states: state, action, probability, and also reward. Right. So this is the Q tables that we use behind this solution. Is to have this Q table which reflects state and actions to come up with kind of long-term learning curves. So there's 2 variables. This gamma basically is the reward rate, right? So we have the gamma, basically the value is between 0 and 1. So if you have 1, basically we want to maximize the future reward. As you can see, this Q basically from next time on. So if the 0 is that we don't interest any kind of long-term reward, yes, minority, yeah, just show interest in the current values. But this R is basically the learning rate. It's also between 0 and 1. So if you have 0, so this is all cancelled out. So there's no learning at all. But if you 1, certainly there's more active learning behind this approach. So the Q learning table basically is formulated as 2 dimensions, right? So this is conventional window size from 3 to 2.5. Basically, we need to decide which conventional window size we need. Depends on the density of traffic. So right has this on row is 3 actions. Whether we keep the same conventional window size for the next transmission, or we double the size, or cut it by half, and also with certain values in between. So certainly in practice, we need to decide what is the maximum optimum values, and then for each transmitter in the next epsilon, they can pick out the maximum value and do the actions, follow with actions. So this is the strategy. So when we talk about the learning-based approach, there are 2 basically actions that need to consider. One is the exploitation, another one is the exploration. Yeah. So basically, exploration is to look at basically what is the best strategy to maximize, you know, your reward. Certainly, you can randomly pick actions. Yeah, because you will never try, for example, certain actions. You want to take a risk to randomize your decision making, which could potentially maximize the benefit, right? Or you can be more conservative, right? Just based on what we have learned so far, you are hesitant to try new ones. But you never know, probably you're going to get a maximum reward. So this is the 2 approaches that this parameter we call is the epsilon greedy strategies to basically look at the tolerance of the randomized decision making, whether you can maximize your Q learning benefit, right? So as you can see, if we have this epsilon values relative on the larger size at the beginning, so it's very fluctuating, which means that all the variables will try to randomize the choices, maximum the benefit. But once we have this epsilon value equal to 0, means that people are not really going to try kind of randomize because they already build up their Q tables. Yeah, so this is equal to alpha. We know that alpha is the learning rate, which means at this point there's no learning. Yeah, so they rely on just purely on their table, which is the value has been formulated, as you can see. So this is the table, the value has been formulated. So don't really want to update the table, just want to use the table, right? So in that sense, you can see the four curves are more stabilized. That's because in these tables, they know exactly what is the maximum values, right, from the Q table. They just always choose that. So no further explanations that we've done. So this is a result. We use one app to simulate performance. As you can see, this is the throughput. Yeah, the y-axis is the simulation time. So we compare different strategies. The bottom one certainly is the standardized DSRC. The top one is actually is the optimal solution, the upper bound. So in practice, you can't really achieve that because the DSRC is the more distributed solution, right? So this is a more centralized optimal upper bound here. But what we can see is that our Q learning based map is collective enforcement basically reward and can achieve the second best performance, which is close to the limit. Certainly, I want to just show to you that the Q learning approach certainly can significantly improve based on the existing solutions. Yeah. So the figure on the right-hand side shows the delay performance. Certainly, you can see the reason that Q learning can achieve better performance is that we can sense the reading environment and increase the contention window size. But with the increasing contention window size, is that you increase your delay. Yeah. So that's why actually from this figure you can see for the standard neutral 11P, because always start from contention window size equal to 3, so smaller contention. But there are significant collisions. It happens. Is this black curve? You can see the maximum throughput or success rate is below 60%, which means that you have a loss of collisions. But your delay can be guaranteed because you always start with contention window straight. But as you can see, Q learning one, so you can significantly increase your collision rate up to 80%. So it means that successful rate is about 80%, but certainly you have a double delay performance, right? So you can tolerate the backup windows, but in the meantime, you can efficient communications between nodes and improve your throughput. Okay, so the next one I want to talk about the security privacy using the blockchain. So I think so far I quickly just give you an overview of in-vehicle communications and also V2X communication using different machine learning and neural network to basically measure the performance, right? And also to maximize the transmission successabilities. So here we talk about the slightly different is slightly on from the upper layer is that once we will have all this the big data, right, generated or transmitted use V2X or other things. So how can we secure our data transmission within the vehicle network? So from the background image, you can see this is more topic to deal with a distributed database. Right now we are focused on more higher layers, but blockchain is more to look at interlinks between all this database. So if you assume that the data can be divided into small blocks, right? The blockchain is how to link each other. So the blockchain certainly is a distributed and encrypted and transparent ledgers containing a log of transactions. The transaction could be just the data, right? So linked to each other and shared across the whole digital network. Certainly, every node, you can see the vehicle, they have their own ledgers, but the ledger should be synchronized. Right? So each node on the network contains a complete of blockchain data. So this is the basic concept behind the blockchain, which is generated from this distributed ledger technology from the distributed database. So when we talk about blockchain, there are different techniques, right, behind it. Probably you've heard of, for example, data structure management, including the linear data structure or non-linear chain, off-chain, on-chain, etc. And also cryptography. So this is more about how to secure the data level transmissions, right, between transmitter and receivers using hash function or digital signature. Usually, this cryptography is all more related with the trust management. For example, we can build up some information-based network or information-less network. Consensus, so I think this is one of the key focus of blockchain networks is to set up the rules to validate transactions in more distributed manner, including proof of work, proof of stake, and also PBIC, practical representing fault tolerance, etc. Incentive mechanism, because the blockchain also primarily relies on individual nodes' behavior or voluntary contributions. How can we create a more friendly or incentive way or positive way to have all the nodes can behavior in a more incentive or positive, honest way, rather than to have this malicious vehicle take advantage of others. So the trust management, like I said, is more related with the cryptographics to view this information for permissionless network, as well as smart contract. So basically, smart contract is a self-executive code. Yeah, so with the term of agreement, the person and record transaction by its own. So basically, the vehicle itself, they can come up. So basically, we can design smart contract and allow all vehicles to follow individually. So this is the relevant techniques behind the blockchain. So when we consider blockchain with the vehicular network, certainly there are three benefits that we can get. For example, is to distributed, because our vehicles are more in the distributed manner scenarios. So this basically allows us to build a distributed ledger. Yeah, the no single organization needed to control all the data, and also the viable solutions can be established for a large number of connected vehicle devices. Second one is encrypted, and we basically can use the robotic encryption method, right, to store all the vehicle data. And each block can contain address of a previous block using this cryptographic hash, right? So it's easier to track in case of any tamper as always. And also transparency. The blockchain can provide this transparency, right? Allow every node to store distributed ledgers. So it's very difficult for a single node try to alter the copies, right? Because it doesn't really have the power to control all the nodes. So just give an example on the right-hand side of what the blockchain service activity looks like. So let's say we have a chart, right? The chart wants to change the length, right? For example, between these two green parts. Then certainly these two green parts have a direct measure of the space availability. If the chart can merge into length, certainly it relies on different sensors, camera sensor, or maybe radar sensors, to basically give an indication or to tell the chart whether it can change or not, right, in a secure way. But for this red part, because it's not directly in a position to justify or verify the space analytics. So in this case, for these red vehicles, it's not eligible for joint decision making. But all these nearby vehicles, as long as they have the sensor data to verify the availability of space, they can basically get involved into a so-called consensus, right, with the requesters, and to jointly decide whether this vehicle can join or not, right? So this is just a simple example of how the blockchain can be used. Suddenly, we apply the blockchain into a vehicular message disseminations. So what this looks like is that, for example, we have car got incident, the car will generate a message to tell the nearby vehicle that, okay, the road is being blocked or whatever. So you need to send a warning message to the nearby vehicle. So the nearby vehicle or incident vehicle who have a visual with the vehicle basically can validate whether this is a true warning message or maybe it's a fake message, right? They can do a consensus and jointly agree whether this message will be further forwarded to many hops away the vehicles, right? So this is certainly gives you an idea of how the blockchain examinations can be formulated. So in this case, we need the nearby vehicle to do a consensus, which is endorsement. Depends on whether they think this is a valid message or incident or not, right? So this is basically consensus, and then we can select the best relay to further forward the data to the further vehicles, right? The vehicles who receive it can basically avoid this traffic jam. So in this case, we transfer the standard blockchain instructions, into the two blocks can be applied into the vehicle domains. One is the reputations, right? Because if the vehicle with a very bad reputation and the Japanese messages, highly likely this is kind of false message, right? So we need to basically do kind of a credit to really punish the vehicle who generate inhonest message, right? So and also these reputations can be basically this credit can be transferred across blocks, right? So the credit will go through from one vehicle maybe to another vehicle. Depends on whether you are the honest vehicle to generate a message. And also the message history, basically, in the meantime, for example, the traffic accident message can be transmitted hop by hop by vehicle, right? So this basically can be recorded through this message history transactions. So in sense that we focus on two words here. One is the consensus. We need to come up with high throughput consensus, which is suitable for vehicle network, and also need to find a way to synchronize the ledger through this consensus. So there are three different types of consensus: proof of work, proof of stake, and voting based. Right? The different actually pros and cons. But certainly for our vehicle mix, we need to have all three basic criteria be satisfied, especially for the time saving, right? For the proof of work, this is typical consensus used by the cryptocurrency Bitcoin, right? Cryptocurrencies, because it involves typically 10 minutes to solve this hash calculation. So this is not really suitable for Bitcoin. You don't have the 10 minutes for just one transaction. Secondly is the proof of stake. Basically, it gives the benefit to the node with the maximum profit, right? The stake basically is the profit. So it's not really a fair solution, the vehicle domain. So basically, we come up with a voting-based solution to satisfy all three criteria and also is time efficient. So this is what it looks like. So when we have the message generated, we have different vehicles. The vehicle can make a decision or job based on whether the message is true or false, and also it can calculate quality factors. The quality factors is not only just make decision on the message itself, it's also to make a measurement of the reading environment, whether for each particular vehicle to have a good coverage of the nearby vehicle or transmission vehicle. So this quality factor can be used to decide which vehicle could be the best to relay to further relay the message into through this traffic pattern. So as you can see here, graph is that every node can do the votings, and each node they can create a micro block. Basically, it's a parallel blocks around the key blocks. So we know that the blockchain needs to be synchronized, right? So you can't really create many different type of blocks across network. This is not manageable. But we do have occasionally have this buffer block because a certain number of vehicles they can have a different view, right? So this is the macro block. But this macro block needs to be actually agreed or synchronized certain stage when we do have basically, for example, to meet this roadside unit, etc., to merge them together into same agreement as a part of the key blocks. Okay, certainly there are some series, for example, along with chain rules to eliminate, for example, if we have duplicated macro blocks or blockchains that to be duplicated or be created because of the dynamic of vehicles. So this is the case is that once we have different macro blocks, we can basically merge them or array into key blocks, right? So this is how we integrate them together, right? Given that we have multiple macro blocks, and then we can compare between these quantity factors, and then finally agree with single key blocks to maintain this basic single ledgers across all the vehicles. So this is performance analysis. We compare different consensus algorithms. So we call this the quality factor. Basically, this is our approach, and then compare with proof of stake and the proof of estimate time. So the parameter just simply follow the standard V2X protocols, DSRC. So we just assume all the vehicle, just disseminate using the DSRC protocols. The figure right-hand side shows the failure in validations. Right? On the top is from 0% to 100, and also we consider different probability of malicious node from 10% to 20%. So the more malicious node you can assume, that's the more challenge consuming to validate the whole transaction, because the majority of the nodes will be non-honest, right? So you can see across different approaches, these failure validations all increase. But for the quality factor, comparatively, it performs best. Of course, the proof of stake and proof of estimate times, simply because we consider the quantity, right, of different individual nodes. And also from these two bottom figures, we show the validation latency, so how much time it takes to validate transactions, right? So, and also the x-axis is number of mining nodes. Mining node basically is the nearby node who can join this consensus actions. So this is basically depends on the different malicious node from 20% to 60%. So if we can just look at 20% node malicious node, then depends on number of mining node. Certainly, we need to we justify the threshold number of nodes who can validate this consensus. But this kind of bound performance just gives you an idea that basically the latency is also increases if we have more mining nodes, because we need more nodes involved into this consensus justification, so which takes more time to agree with the result. And also, if we have a more malicious node, you can see that this latency is significantly worse than the previous one, simply because majority of nodes are malicious node, right? How can you eliminate malicious node? It takes more time, and also need more threshold node that agree with a valid result. So that's why it takes more time. Yeah, so this is another slightly different approach. Is about using the federal learning combined with blockchain. So we know that even for the blockchain, we need to involve lots of data exchange, right, between vehicles. But this is not really a secure privacy way, because when you exchange your information and the data, for example, your locations and speed, this is some privacy issue related. Rather than exchange the data, we exchange the model, right? So this is the idea behind the federal learning, is that in every vehicle, they can train their models, right? So this is a neural network model using their own personal data. And then what they exchange in the vehicle is their neural network model. And the model can be further uploaded to the central server, and the central server can aggregate them together into a global model. So what this looks like is based on our previous work, is that we also come up with basically improve or further learning. In that sense, is that the vehicle, they only need to exchange their training model. So the model basically has a number of input, including your vehicle speed, right, and also your video environment, and also your directions, etc. And the output of the model is basically is a number of acknowledgement information that you can receive. So that the acknowledgement basically we convert it as a type of score, basically how good that utilization is, and then allow to hear and exchange your nearby vehicles. So that score basically can be used to decide in a more centralized way when you have a global model, which vehicle can be selected as the trust, let's say, relay node or the minor node, right, to forward as a consensus. And also we do have this basically this smart contract that we pair up basically on each vehicle. Because now we don't really rely on the vehicle data being exchanged, right? Because it's a model. So some vehicles, they need, you can assume if it's a malicious vehicle, they can maybe create some false data to benefit or take advantage of self from others. Because you don't really have a real data in the training model, you come up with the false data. So the smart contract will validate whether the data you generated is true or false. Okay? And then we can use this kind of smart contract to regulate the security aspect of this data trainings, and then come up with this global model, and then integrate together as a global model. So this is the result. As you can see, without security, which means that we don't really find a security check. So this security check is basically related to the smart contract. So without security, it takes longer iterations to minimize the total loss. Okay, so the total loss basically is the errors between the real data, real result, and also predicted result. With security is that once we include this smart contract, basically you can get rid of, remove all these false claims and false data. And so this conversion via the whole network takes less time, right? So this is total loss can be better improved in terms of the whole prediction and also message dissemination. So we use OMNet as well to run the simulations, and these figures gives you the time delay against with percentage malicious vehicles. So we can see is that the proposed solution, which is the federal learning, doesn't really fluctuate too much. No matter how many malicious node, percentage malicious node you have, simply because all these model training base they are running separately or independently, doesn't really too much effort by this number of malicious vehicles. It's more like training being done real time and separately. But for this polling factors, so we know that because once you have increases the number of malicious vehicles, certainly we affect the threshold how we do the voting. So it will take longer time to agree with the result. But for this further learning one, because this model has been trained all the time, you don't really need to find another time to agree with the model. So this model one is more stabilized. No matter how many percentage malicious vehicles that may exist. The voting base and also another one is further learning base. Right, so I think I already run out of time, so I just want to take you another example work that we have, which is not quite relevant with the Vehicular network, but it could be more relevant application. One is about flooding, so we combine IoT to optimize this flooding kind of disaster monitoring. So this is a use case typically happens in UK, when flooding happens, the road infrastructure has been destroyed or blocked. So we come up with some solutions is to deploy a number of sensors. You can see here is the water level sensor radar sensors to combine with some hydrological hydrologists, for example, model approach, collaborating with other colleagues to basically feedback input data for their model trainings, so that they can come up with a prediction model to predict basically what will be the risk of potential upcoming floodings, given, for example, the soil humidity data and the water level data, and also rainfall sort of data that is collected from various sensors, and then feedback into the model trainings, and then we can give further predictions and also warnings to the nearby vehicles to avoid, for example, the traffic scenario that is trapped by the flooding scenario. So this is one project that we have done with different discipline researchers. Also, we have another one is to look at this robotic teleoperation system, a kind of physical therapies, right? Post-COVID recovery solutions. The background is that because of COVID, even in the health domain, and so we don't really have too many face-to-face opportunities, especially in shortage of home care, and also we do have patients, for example, with a stroke or brain damage, need kind of recovery therapies. In that sense, that with the robotics technologies and also with 5G wireless networks, is that the patient they can do recovery relies on what's on the home. And remotely, the doctors or physiotherapists, they can basically remotely control what arm, and then in the meantime, the patient can basically get the same benefits as a face-to-face recovery process. Yeah. So in the middle, in this case, we rely on in this case it's Wi-Fi, but we're probably using 5G private network solutions to build up this kind of robotic synergies, right, for physiotherapies. So I don't have a video, but I think probably it's not really working this time. Yeah.
Okay, so this is a demonstration of our.
So I think I speed that. So basically, you can get a sense that is these two robots can remotely be synchronized. Yeah, to do it. I think that's close to the end of my presentation. Also, in the meantime, we do have some hardware-based vehicular network and IoT use case. For example, we have this ESRC and we connected with traffic light, so we can have our vehicles to get this traffic light counting down some sort of services from a mobile phone and also a autonomous vehicle. Now we're more looking at the drone-based V2X network, right, including this drone vehicle communications. Yeah, so I think that's all for today for my sharing, and thank you so much. Any
Thank you, Dr. Cheng. So any questions? You can post it in the chat. And any question you can
ask. Message or not, but not all the vehicle could be the miner, because if you don't really have a visual or don't have any sensor to validate whether this is a true accident or not, they are not claimed as the miner. But only the nearby vehicles can be a valid miner, and then they can do a drawn consensus. The consensus is like the voting. Yeah. So if I say, oh, this is a true accident, I say yes, and another vehicle say no. So they can collectively receive a number of this sort of result. So we can dynamically set a threshold. If we, let's say, receive five yes, then we say this is a true warning or the true message, right? If less than that, we say this is the false message. Yeah. So the miners are primarily a vehicle, nearby vehicle, who has capabilities to verify the incident. Yeah. But we don't restrict whether the miner a vehicle or maybe roadside unit. I think both of them are equally can be the miner. But in our case, because we are not really focused on the infrastructure itself, it's just simply message dissemination as a vehicle itself. The vehicle should be powerful enough to be a miner. Yeah. Very interesting topic. Any other questions from
So there is a question. There's a question in the chat. So the question is, do you see computing power vehicles can potentially be a trading commodity?
Yeah, I think that's a good question. So I think in terms of computing power, I think the vehicle should be at the moment, the modern vehicle should be very powerful enough, behaving as any agent node to compute very sophisticated computing tasks, right? No matter is AI or maybe image processing, etc. So I think from that point of view, there's the trading community. I think this is this potential, yeah, to doing that. But I think it's more related to what sort of the use case, yeah, whether you want to build up to involve vehicle a part of this trading kind of cases. Yeah, but I think from the computing point of view, I tend to believe that the vehicle itself will be very powerful, yeah, to deal with any standard or even beyond complicated computing tasks. I think that should be for sure. Yeah.
Thanks for the question. There's another question. Yeah. Compute. Yeah. Just right here. So you can ask your question.
Yes, I have a few questions.
Yeah.
First of all, is there any compatibility between DSRC and then 5G? For example, is it possible to perform vertical handovers between DSRC and LTE? Oh, sorry, 5G.
Yeah, I think at the moment they are competitive solutions. I don't think at the moment the industry looking at to harmonize it. So because one is the infrastructure, DSRC is the infrastructure-less communications. But for the 5G, for example, this relies on the infrastructure 5G radios. But also for the 5G, let's say their standards. At the moment for V2X, they also have their own solution as a part of there's 5G to look at this V2V communication. They use this side channel to deliver exactly what DSRC is doing. So this is, I think, this a more competitive solution between each other, and also some space they want to integrate, but not from these two technologies together, but from one single dominant, let's say cellular CGPP. So they want to have their own solutions to accommodate both infrastructure-less communication and also their infrastructure communication. Yeah.
Could you please go to slide 29? Yeah. If you use, for example, topology-based routing protocols like OSR, AODVD, and like this, can we have any change in throughput? Can we make any significant improvement in the throughput?
I think the challenge for the method that you mentioned, whether they can deal with this high dynamics of vehicle transmission and also the overhead. Yeah. So this is something that you need to simulate or maybe to find a way to validate. Because I think in this result, we don't really make any pure assumptions of routing because it's a pure dynamic. So we do have some traffic models. So this is from the Sumo. Basically, they can simulate this kind of vehicle dynamics. And then on top of all this overhead from things like WP. But regarding to the routing protocol that you mentioned, it's also need to look at whether maybe the overhead is more overwhelming than this standard DSRC because it doesn't really rely on any, because this is broadcasting based. So for the routing protocol that you mentioned, probably there's some overhead handshaking that needed. So that will kill the throughput. Yeah. So maybe potentially you show worse performance or very different performance, but you need to look at the overhead, how protocol that you mentioned are basically formulated. But I think there's a reason that why there's the DSRC one, because the fluid dynamics to make this more broadcast-based, more suitable for certain V2V applications. For the LTV that you mentioned, probably this is more multi-hop, based routing strategy. Whether they will be suitable for vehicle, and you need to find out.
Right. Can I ask you a question?
Yes. Yeah.
Okay, from USM. Is with regards to the blockchain-based message dissemination.
Yeah.
I've noticed that the results, the lowest performance was somewhere around 100 milliseconds, if I'm not mistaken. If you go back to the results, the message, so blockchain-based.
Is this one?
Maybe the other one before. Yeah, this one. Yeah.
Yeah.
So does this also include a message being disseminated?
Let me see.
The delay for message dissemination.
Yeah. I think this result. I think this result primarily is to look at the delay of verifying the result of verifying the consensus. Yeah. It's not really. I think it's not really to measuring the message dissemination itself, but it's more like to the consensus overhead that being. Yeah.
Okay, so the thing is, right, even with this method applied, the delay will be somewhere, I think, around 100 milliseconds, the best case scenario.
Yeah.
And if you look at the 5G, especially the vehicle safety performance limits, where it's somewhere around between 3 milliseconds to 10 milliseconds. My question is, having all this, blockchain-based kind of technique, and achieving the results you have, do you think it's for now it's just still too early to consider all this method? Given that the performance limits provided by 5G standards is very low, and it's very small in terms of its delay.
Yeah, so I think that's a very good question. So I think at the moment, so what we are basically looking at in our study is to look at the opportunity combining the blockchain with the vehicular network communications, whether there's the possibilities, to utilize the blockchain to secure the communication and also provide these privacies. So from that sense, I think it's not really entirely just the communications problem. If we are just dealing with, for example, one-hop communications, no matter what sort of data that you transmit, certainly the industrialized, you just mentioned that their 3GPP has defined, for example, 2 milliseconds or 3 milliseconds, but that requirement is more on the link level or transmission requirement. Yeah, but from the service level, there could be slightly different or even relax the requirement. So I think in our papers, I think we mentioned, it's just one example, right? I just give one example is that for certain applications, the whole delays can be tolerant up to 1 second, but certainly this is not really a communication kind of requirement. It is more from the application's point of view. So in that sense, we I think tentatively believe that the blockchain can contribute, but it's also need to be looked at the overall system requirement in terms of applications, because in some case for this blockchain type of services doesn't really need to be behavior as an application that need to be fully synchronized and be delivered under a millisecond, because in some cases we can have these real communications and also real processing can be conducted individually and then synchronize, like I mentioned, the key blocks at a later stage. So this doesn't really necessarily be fully synchronized at the same time in real time. So this is also related with the different use cases and also the how this internal process and the data basically the synchronization need to be organized behind these ideas. But I think that's a good question to really think not only just from communication point of view and also from applications point of view. So what are the opportunities? Yeah.
Because I think the thing is the CAM message generation itself, the minimum requirement is every 100 milliseconds.
Yeah.
So we've done some work here. We found that I think it's too very strict in terms of delay requirements provided from the upper layer.
Yeah. So I think communication-wise, certainly there's a time restriction, for example, in terms of millisecond. But if it's down to the applications, for example, message warning disseminations, or even let's say in real traffic accidents, so that probably from people's perception and also from top layers point of view, it doesn't really necessarily to be, or there's no much difference between 10 millisecond or 100 millisecond from people perceptions. So that I think there's some space that can leave for not only just communication and also computations, to handle the overall use experience and also the task. But I think I agree with you that certainly communication and also the data management that can be treated or looked at together. Yeah, and to deliver and to jointly agree with let's say deadlines which could be suitable for vehicular, let's say message dissemination or any sort of emergency services. So I think that's still a work that needs to be done.
All right, thanks a lot.
Yeah, thank you.
I think we have. So about the recording, we need to ask the permission to share to you. So at this moment, we do not. So we will probably end this if there is no more question. Thank you so much, everyone, for coming. This is a very good opportunity to listen to Dr. Zhang.
Okay, thank you everyone.
Thank you so much.
Yeah, thank you.